So this is reaction. This is from exam 3, 2015, number 8. And the question kind of is on the floor about intermediates and recognizing those. Right? So you can't really recognize the intermediates until you start doing the mechanism. So until you start doing the mechanism, you don't know how many intermediates you're going to have. So let's follow our rules. Things we need to do. What do we need to do? We need to number our carbons. Certainly number our carbons on our alkene. We need to do what else do we need to do? Add in lone pairs, so the chlorine. What else do we need to do? Yep, so add hydrogens first where? On the alkene, add the hydrogens on the alkene. And then, once we've done all that, now we're to the step where we want to use arrows. And how do we know where? So to figure out where the arrows work, we need to identify what? Electrophiles and nucleophiles. So what's my nucleophile going to be here? The pi bond. What's my electrophile? Where's it delta plus at? The hydrogen. 2 electrons go to that H. These 2 electrons go to the chlorine. We're going to need to form a carbocation here, or we're going to form a new CH bond as well. Where do you want the CH bond to be at? You want the new CH bond to be on carbon, carbon 2. The new CH bond should be on carbon 2, because then your carbocation is on carbon 1. Does carbon 1 still have this hydrogen bonded to it? Yes, it does. Now carbon 2 has 3 hydrogens on it, just to remind ourselves. What else am I forgetting here? So the last step of the reaction mechanism rules is what? Balance your charge. So what am I missing? So all of a sudden I have a plus charge. Did I start with a plus charge over here? So what do I need to have in there too? The Cl minus. Right, do we see why the chlorine has a minus charge? Right, see how the chlorine here got electrons? Right, it received a lone pair of electrons. So now it started with 1, 2, 3, now it has 1, 2, 3, 4. So it's a negative charge. Right now at this point I think I forgot something up here. There is a solvent involved, and we'll deal with that in a second. But what do we know about solvents as far as reaction rates and what's going to happen with solvents? Solvents there's a lot of them, right? There's a lot of this ethanol in this case, right? So that's a high concentration of that. So that's maybe going to play a role here in what ends up being our nucleophile in one of these steps. But in the meantime, we've made a carbocation, right? What kind of carbocation do we make? A secondary, right? This carbon 1 is bound to 2 other carbons. So we'd be thinking about rearrangements, right? Only way we're going to rearrange those is we make something more stable than a secondary. So what could be more stable than a secondary? Tertiary or? No, don't forget, what are the ways to stabilize carbocations? What kind of resonance? There's 2. Lone pair and pi bond, right? So don't forget those 2 as well. Right, so what we've done here is we've created a secondary carbocation. We're thinking about rearrangements. And we've also created our first intermediate, right? So this arrow right here shows, right, and these mechanism arrows show a transition state, because this is showing, what do these arrows represent? These mechanism arrows represent the making and breaking of bonds, which is a transition state at the top of a hill. And what happens after a transition state? You make an intermediate. So this, right, these 2 things together, but really the carbocation piece is an intermediate. We'll call that intermediate A, because that's the first one. It's called intermediate A. Now we think a shift can happen, right? So we want to look to our hyperconjugation buddies for those shifts. So hyperconjugation buddies are how far away? 2 sigma bonds away. So 1, 2, or 1, 2, or 1, 2. So how do I pick between those 3 hyperconjugation buddies? Are these all the same, or are they different? They're all the same, so it doesn't matter which one I pick. All right, so I'll just pick this one. I'm going to label this carbon 3 and 4. Right, so we're moving carbon 3. Carbon 3 is going to be what in this reaction? In this mechanism step, what is carbon 3? A nucleophile or electrophile? If you're not sure, What is carbon 1 for sure? It has a plus charge. So it's for sure an electrophile. So what does carbon 3 have to be then? It has to be the nucleophile, right? So let's have those electrons move with carbon 3. So what new bond did I form? I made a carbon-carbon bond between which two carbons? 1 and 3. There's 3. There's 4. Where does the plus charge go? I guess I'll call this carbon 5. Carbon 5 has the plus charge now, right? Carbon 5 is the one that lost electrons. Do plus charges move? No. Electrons move. That's right. Have we balanced our charge? You gotta have the chlorine along for the ride. Cl minus is along for the ride. Now, right? We've done again. What have we done? We've broken and made bonds. So that would necessarily be a transition state. So right here was transition state 1. This would be transition state 2. So we have 2 heights of hills, 2 hills. What did we just make after transition state 2? We made intermediate B. All right, intermediate B. So we have transition states. All right. Now with intermediate B, are we good with our carbocation? No. So it's a tertiary carbocation. The only way I can make this better is what? Lone pair resonance or pi bond resonance. Do you have lone pairs or pi bonds? Nope. Can't do it. So this is it. I'm stuck. Now the question is, okay, I know my carbocation is what? What is carbon 5? Is it an electrophile or a nucleophile? It's an electrophile. Now the question is, what's going to go after that? What's going to be my nucleophile? Now, if there was no solvent, Cl minus looks pretty good, right? Chlorine with a minus charge, right? Chlorine's that's decent, right? Nucleophile, negative charge. But if you were in a solvent, right? How much more solvent is there than Cl minus? A lot, right? So even though Cl minus is a better, more reactive nucleophile, it doesn't matter, right? You can have the greatest nucleophile in the world, but if there's a billion bad ones, the bad ones are gonna win, right? It's not enough to overcome it. So what's gonna happen here is one of these solvent molecules is gonna end up being the nucleophile. Now, where on this solvent molecule is it nucleophilic? Oxygen, specifically on the lone pairs. One thing to notice here with that arrow, did I break this oxygen-hydrogen bond? Did I break this oxygen-carbon bond? Then you shouldn't do that either. Don't do that. Right? What's the nucleophile? The nucleophile was the lone pair. The electrophile was carbon 5. So we just made and broke bonds. So we did what? We did another what? Transition state. So it'd be transition state 3, right? Every transition state is when you make and break bonds, right? What do we make here? What's our product look like now? Number of carbons, 1, 2, 3, 4, 5. What new bond did we make? Oxygen to carbon 5. And don't forget that hydrogen's still there, right? Okay, am I good? What am I missing? I'm missing chlorine, okay. Cl minus, good. Plus charge needs to be where? On the oxygen, excellent. Right, why is there a plus charge in the oxygen? Notice the oxygen is the one giving up a lone pair. Right, also now the oxygen has how many bonds? The oxygen has 3 bonds. How many bonds does oxygen want to have? 2. Okay, so now one last step here. So this is intermediate what now? We've made another intermediate. Intermediate C. What's the final step here? Are we going to leave that oxygen with the plus charge? Nope. You can use the chlorine to go grab it, or you can just say, right, this H is just saying it's okay, oxygen. Take the electrons. Another transition state. We broke or made a bond. Transition state 4. What have we made? what's our final product? What kind of functional group did we just make? We made an ether. And we made H+. Right, so to balance our charge, what did we create? We made H+. And what do I need to make sure I bring along for the ride again? Cl-. Now some people say, well, wait a second, won't those react? They will. I mean, if you had HCl, HCl is what kind of acid? It's one of the strong acids. So what do you guys know about strong acids? What do? They fully dissociate. So, right, drawing it as H+ and Cl-, that's the same as drawing it as HCl. Right, because HCl is a strong acid. So it just becomes H+. So this final thing then would not be an intermediate, so we'd have this is the final product. So let's do a free energy diagram of this bad boy now. So let's label this product. Free energy diagram. So energy or potential energy, reaction coordinate. You don't really know anything about the starting materials and the products. I didn't tell you anything about delta G, did I? So you really don't know the relationship, so just make them the same. Right, so say the starting material and the product can be the same energy level. If you don't know, you just don't know. Right? Which of my intermediates is going to be the highest energy? Which of my intermediates is going to be the highest energy? I would guess, I'll make this smaller, get things out of the way. What intermediate is going to be the highest energy? A. Why? Because it's carbocation, so it doesn't have a what? Carbocations do not have full octets, and it's a secondary one. So that would be higher energy than a tertiary one, which we also made. That was intermediate B. So if I even just drew them in, I would say, okay, so here's int A. There's int B. And then what about intermediate C? That's going to be probably pretty, yeah, that's going to be the lowest, right? Because everybody there has a full octet. Now I just need to fill in the hills, the transition states. What's going to be the hardest one to make? The A, right? Because we're making a carbocation. Next one, that's going to be working downhill now, right? We're going lower in energies. So that's going to be a short activation energy. That's going to be a little hill, right? This would be a little hill, whereas this is a big hill. And then finally, this one down will be even probably fastest yet. And then finally, we'll turn intermediate C, that H falls off, and we get our products. So in this case, we had 1, 2, 3 intermediates, and we had 1, 2, 3, 4 transition states. So this is working on a sapling problem. This is number 6 and part 2 for the alkene reactions. What do you need to do? All the rules are what? Numbering our carbons. Someone's going to 1, 2, add in lone pairs. What else do we need to do? Hydrogen's where? On the alkene, the pi bond. Good. So in this case, we have Cl2. This is when we make those triangles, the bromonium ions or chloronium ions. So it involves 3 arrows. Remember the thing about chlorine, right? The evil twin, and I didn't tell you guys this. So imagine I have an evil twin, and it's because he's evil, he's super delta minus. Whereas I'm, of course, always on the positive delta plus. So even though we're exactly the same, our relationship is such that at any one point, maybe one of us is more negative than the other. So this chlorine, right, because it's polarizable, right, even though we're exactly the same, at one point this chlorine can be more delta plus and this will be more delta minus. The nucleophile here is what? It's going to be the pi bond still, because that's what we've always been doing. The pi bond is going to attack this delta plus chlorine, right, the good twin, me. And at the same time, this chlorine-chlorine bond is going to break. But then again, chlorine's not going to let that stand, right? I'm going to come back and say, well, I'm so long, bad twin. I'm coming back and binding to one of those carbons, 1 or 2. It doesn't matter which one I go to, right? This third arrow here, I can have it go to 2 or 1. It's fine, either way. Either way is fine. Now, the stereochemistry part of this is important. What is the hybridization state of carbon 1 and 2? What are their hybridization states? sp2. So what's their geometry? planar. So the Cl can come from the top or it can come from the bottom. So you're going to get both of those enantiomers. So as I redraw this, I need to be cognizant of something. This ring and this methyl, if I enable this methyl 3, they're both on the same side of the double bond, aren't they? So when I redraw this, I'm going to redraw it with wedges and hatches, where that cyclohexyl, that ring, and carbon 3 are on the same side. They're both wedged. That's a wedge. That's a wedge. That's a wedge. Now in that same sense, this methyl and this H are both on the same side of the alkene, so they'll both be hatched. Now I like to do it this way because it's easy for me to, I don't have to, once I set the wedges and hatches, I don't have to change that ever. It's done. I don't have to mess with it. So this was carbon 1 and this was carbon 2. So the chlorine is going to be on the top. And you're going to have the exact same thing with the chlorine on the bottom. I'm not going to redraw it. Take the time to redraw it yourself, right? Basically do the exact same wedges and hatches, right? But just put the chlorine on the bottom side, right? So both intermediates will be possible. Now let's talk about, do we balance our charge? Cl minus is floating around. But again, we need to think about that thing on the bottom of the arrow, right? That's what? Things on below and the bottom of the arrow are solvents. And there's a lot of them. So this solvent, let's draw another solvent, is probably going to be the one that's going to react here. And the chlorine, do you think the chlorine is happy with the plus charge and being a 3-membered ring? No. So carbon 1 and 2 are probably both very delta plus, right? Even though the chlorine has a plus charge, where is it electrophilic? So chlorine has a plus charge, fine. But if you saw a carbon-chlorine bond, who has the electrons? Carbon or chlorine? Who has the electrons? Chlorine always does. So each carbon 1 and carbon 2 are both very delta plus. But are they the same? So what's the difference between carbon 1 and carbon 2? One's more substituted. Literally, carbon 1 is more substituted. So that's the one that's going to be the electrophile. That's the one that's going to be able to stabilize the delta plus charge more, carbon 1. So that's where the lone pairs on the solvent are going to react there. Now there's something else though. From what angle are they going to attack? The opposite side. Why is that? Why are they going to attack? Why does this have to go from the back side? Because that's where the anti-bonding orbital is. Remember, where's sigma star? Sigma star is 180 degrees away from the sigma bond. So as the lone pairs here react with carbon 1, what's going to happen? The bond between carbon 1 and this chlorine, those two electrons are going to go to the chlorine. Common mistakes I see, people will have this react here, have the lone pair attack carbon 1, and all of a sudden they'll want to break this bond. Don't do that. As this lone pair in the oxygen reacts with carbon 1, this carbon-chlorine bond must break. And it's going to react in such a way that it's coming from a backside, so it's going to be, what do we call that? What's the final relationship going to be? The chlorine and this oxygen are going to be what to each other? Trans or anti. So the reason why this carbon is more reactive is because, essentially, because it's more substituted, right, this bond can be weaker, which makes this thing more delta plus, right? So it's really just about, like, kind of that same argument about hyperconjugation type stuff. But is there a carbocation here? Oh my God, is there a carbocation? No carbocations, no carbocations, okay? Okay, got the product made here. So carbon 1, carbon 2, carbon 3. What am I missing? Missing a couple things. I'm making common errors. I'm showing you common errors. Where's what? The H should be on the oxygen. People will forget to do that. Then Cl minus is along Friday. We're still not there yet. And the plus charge on the oxygen. Very good. Am I done? No. Nope. So we had a transition state 1. We had an intermediate A. We had transition state 2. We have an intermediate B. And then this H needs to fall off. And that will give us our final what product? So another transition state 3. And then our final product would be, what is our final product functional group going to be? It's an ether. Don't lose carbons. And what other product would be in this as well that I haven't drawn here? The plus, H plus, and Cl minus. But what else? I didn't just make this version. I also made the enantiomer, right? Right, because initially I would have the other chloronium ion on the bottom. So I'd also have the other enantiomer where this chlorine would be down and this oxygen would be up. So don't forget, you're making a racemic mixture here. Okay, so working on a sapling problem, part 2, number 5. So the hard part here is we're going to work backwards. So we're given a product, and we're saying what is the starting material. So you have two products actually. You have this ether, right? Cyclic ether with a bromine, and you also have HBr. Those are your two byproducts. Now, we've been doing all sorts of reactions with alkenes. So these should be thinking in your head, alkene. You should be thinking that. The other thing you should do, right? Don't forget your basic stuff. What's the first thing you should always do? Number your carbons. Let's just number those carbons. 1, 2, 3, 4, 5. Number those carbons. Right? Add in lone pairs. Great. So as we work backwards, we know we're thinking alkene, right? We're for sure thinking alkene. We need to look at the product and say, okay, where is the stuff at in the product? Essentially, where are the functional groups? Where's the stuff at? Right? If you looked at this molecule, where would you say which carbons has stuff on it besides carbon? Carbon 1 and 2, right? Looks like carbon 1 and 2 has 2 things on it, right? So that would make me think maybe there was what between carbon 1 and 2? The pi bond, right? The pi bond was there. Also, if you've been doing a reaction sheet, you had a bromine and you added and you made an ether. That's a very specific, right, type of reaction product. You've been maybe writing down. Right? If you go back and look at that Unit 1 reaction review, I talk about that, right? It's also in your study guide. The hard part here is usually we're used to, right, the ether being formed coming from what? The ether is usually being formed, but where is it usually coming from? The solvent. This solvent is not an alcohol. So the weird part here is the ether is coming, but it's not coming from the solvent. So that means it must be an intramolecular reaction. That everything must have already been in place here. Right? The ether, this oxygen, right, where's this oxygen coming from? Do you see it in the reagents? Right? So if the oxygen is not in the reagents, it had to already be there. Right? It had to be there from the start. If you see this oxygen here and you don't see an oxygen in these reagents, the oxygen must have been in the starting material. Right? It had to have been. Okay? So let's think about the 2 bonds you made, right? Because we know it's an addition reaction, right? We've been doing addition reactions. What are the 2 bonds you made? So you made a sigma bond between C1 and Br. So these are bonds that are formed. And then you made a sigma bond between what else? Oh, hydrogen and bromine, yes. And then what's the other sigma bond you made? C2 and oxygen. Right? You can kind of look at this and say, well, right, where's the action at? It's between carbon 1 and 2. That's where the functional group's at, bromines and oxygens. So those must have been the bonds that we formed. Right? And we also said the oxygen isn't present in the reagents. It isn't one of the solvents. So this oxygen must have been present in the starting material to begin with. So let's draw some squiggly lines saying, okay, we know we're breaking that bond, and we know we're breaking that bond, and we know where this bond came from somewhere too. So I draw this, it's called retrosynthetic arrow. What I have, we talked about the pi bond being between which two carbons?
1 and 2.
1 and 2. Let's put the pi bond between 1 and 2 then. The oxygen we said was there from the start, right? So let's number our carbons again. 5, 4, 3, 2, 1. So now we're kind of stuck here. Okay, so we know there has to be a bromine somewhere along the line, right, and an oxygen. So I've kind of just broken these bonds and put a pi bond there. But let's take a step back and think about electrophiles and nucleophiles. When you have Br2, what does Br2 do to the alcohol, to the alkene, excuse me? What does Br2 do to the alkene? What does it turn those carbons into? Electrophiles or nucleophiles? So when Br2 adds normally, I'm just going to draw a generic Br2. So if I have a Br2 or a bromonium ion, right? Br2 makes bromonium ions? Yes? Yep. What did the bromonium ion turn carbon 1 and carbon 2 into? Because initially that pi bond was a nucleophile, but now they're both electrophiles. Right? Everybody see that? So if that's the case, right? So that means we're going to turn both carbon 1 and carbon 2 into electrophiles in this case. What does the oxygen need to be then? If these are both going to be electrophiles, the oxygen has to be a nucleophile. Now, we can take another step back and say, well, I can't just have oxygen by itself, right? We don't start with a charge. You could maybe think the oxygen has an H on it because we're still missing what? We're missing an H here, and we're missing a Br. Yep, it's tough. It's tough. Right, this is the tough stuff. Working backwards is tough. But you're kind of taking a step back and really remembering all sorts of things, right? You're remembering I'm making pi bonds, right? I'm adding things to pi bonds. What are the two things I'm going to add? When I make a bromonium ion, which you should recognize, when you see Br2, you should automatically think, well, bromonium ion. And what does that bromonium ion do to the carbons that were alkenes? It turns them into electrophiles. So this is actually the starting material. This is the product. This is the right answer. This right here. Now, the best thing you could do, and some people say, well, how do you know that for sure? Try it. Say, okay, I'm going to try this as my starting material. Do the mechanism, see if you get this product. See if you get these two things. Right? The best way to check it is to try it. Right? Otherwise, it's too hard to just look at a lot of times. You have to actually try it yourself. So does everybody see that? Maybe it'll look clear now. It's a tough one, absolutely. But the best thing is once you have an idea, once you have an answer, try it. All right, this is a sapling question number 8 and part 3 in the alkenes. First thing we want to do, number our carbons. So 1 and 2 for sure about the pi bond. What else do we need to add? Lone pair is not really an issue. Hydrogen that's on the alkene always. You want to add those hydrogens? Now you should be able to look at this right away and just draw two products.
Yeah.
So let's take a couple of seconds to see if we can do that. So for this one, let's see. Right, so for this one, we're doing B2H6, which is the same as BH3, right? Anytime you see boron and hydrogen, just think that's what's going to do hydroboration. Second step is H2O2, which is just the replacing part. You need to know the mechanism for the first part. I'm not going to show you the mechanism for the first part here. I've done it before. You can find that. The biggest thing we're going to talk about here, though, is what type of products we're going to form as terms of regioselectivity and stereoselectivity. So let's talk about regioselectivity first. So we have carbon 1 and carbon 2. Are carbon 1 and carbon 2 the exact same types of carbons on that alkene. So what region of the alkene are we going to select for here? Carbon 1 or carbon 2? The more substituted or the less substituted? The less substituted, right? BH3 goes for the less substituted, right? Good. So maybe we'll put a note here. I need to end my OH needs to end up for sure on carbon 2, right? Because we know we're adding alcohols here. That's what we do with this reaction creates an alcohol. And we know it needs to add to carbon 2. Now the question is, when we do this BH3 or B2H6, how does it add? Right, so we know the OH is going to end up on carbon 2, but does it add, is there a carbocation? Does it add syn? Does it add anti? So does it have a carbocation? No carbocation. Does it add anti? No, it adds syn or cis. So the boron and the hydrogen add on the same side. So which carbon is going to get the hydrogen, right? So overall we're adding two. We're adding two things. The first step, we're adding a BH2 and a hydrogen. And then the second step, we're just replacing that BH2 with an OH. So which carbon is going to get the new hydrogen? Carbon 1. So when I draw this, right, because the pi bond, what's the hybridization state of these two carbons?
sp2.
And that geometry would be? Right, so it's flat, so the boron can come from the top or it can come from the bottom. Right, so we're going to have to draw wedges and hatches now. So 1, 2. So let's say the boron adds from let's do the bottom one first. So the H is going to be here. Then what's going to be cis or syn to the H? The OH. Right? The OH and the H added syn. And notice the OH, of course, end on the less substituted carbon. Now what's the other product we need to draw here? Because the boron will come from the bottom, but it also could come from the, oops. It could also come from the top. Is the OH and the end, is the OH and the H always on the same side? They have to be. And the OH is always on which carbon? Carbon 2. So there's the OH and an H. So that means there's an H here, and that methyl, right, is not on the same side. Right? So this H and this OH has to be on the same side. And what is the relationship? What are these to each other? They are enantiomers. Because they have their chiral centers are opposite. They're mirror images of each other. Absolutely.
You can draw this without changing the wedges and hatches, right? You know what I mean?
So I could draw this. So this is one way. This is a quick way. I could also draw it. Right, if you were asked to do the mechanism, it might be easier to draw it like this. The final product would be, you could also draw it like this, and this would be correct, plus it's an enantiomer. You could also draw it like that too. Yes?
So, and that way you don't have to change anything?
Yep, that way, and if I drew it this way, the only other one I'd have to draw would be one, 2, 3, 4. So these two are enantiomers to each other, and these two are enantiomers to each other, and this one and this one are exactly the same thing, and this one are exactly the same thing, just drawn different ways. But if you do R and S for those, they'll be exactly the same thing, right? So you can draw things different ways and be exactly the same thing, right? Because of the wedges and hatches.